Hello all and welcome back to this course on digital systems. So having looked at the idea of a flip-flop and designing sequential circuits and analyzing sequential circuits in the last couple of weeks. Hello all and welcome back to this course on digital systems. Having looked at the idea of a flip-flop and designing and analyzing sequential circuits over the last couple of weeks, it is good to conclude this course with the idea of pipelining. In fact, this is where you will actually understand why a flip-flop is called a sequential element, right? The flip-flop can technically store data. It can be used as a memory also. If you want to store a 1 or 0, you just write it and then hold the data forever. That is also a memory. But the point is, in a sequential circuit, we want the data to be sequenced in a particular order, the order in which it arrives, okay? And that's why it is called a sequential element in the first place, which will become amply clear when we go through the idea of pipelining and sequencing in general. So let's start with the most basic idea of pipelining, okay? We got to ask ourselves, where have we seen this? Okay, the idea of a pipeline comes from a factory setting where, for example, if you're manufacturing a car, right, somebody adds the wheel to it, somebody else basically tightens the screws, right, somebody else fills the air, and things move on like that, right? So a car is sent in, and then people do different things and the car comes out, and this enables a certain advantage which we will see what exactly it is, okay? But closer to home, all of us have definitely seen a very innovative application of pipelining, okay? So I will just talk about that. Let's say that you have a building which is under construction here, okay? Some building under construction, and I have let me use red for this. I have a bunch of bricks which are placed here like this, one on top of the other. Okay. So I have 1, 2, 3, 4, 5, 6, 7, and so on, right? And the idea is, of course, the building which is under construction has been constructed until the first floor, and these bricks need to reach the top, right, of the first floor. So this is, let's say, this is not like a multi-storied building that we are talking about. We are talking about a small house with just 2 floors or something like that, right, where they don't have the luxury of putting a lift and stuff to take material up, right? So what do the construction workers do in that case? Well, of course, what do they do is, assuming that this building already has some sort of a staircase, it would go like this, right? So let's say it is built like this, and there are stairs that have been built to go all the way to the first floor. So of course, the most naive way of doing this is that you take one brick at a time, right, and then go walk up all the all the stairs, leave the brick on top, come back, take the next brick and go, right? So this is something that we could technically do. Oh, by the way, let me also not number it like this because it can be quite confusing. So let me number it the other way, because I cannot pick brick number 1 in that case. Sorry. This is brick 1, 2, 3, 4, 5, 6, 7, 8. Brick number 8, right? So yes, right? But obviously we know that the construction workers do this far more efficiently, right? So what they do is they simply line up on these uh, stairs here one by one. So there is one construction worker per stair like this, right? You go all the way, there's one more here, and final person here who's going to receive this brick, and then they're going to accumulate the bricks on top there, right? So now there are certain constraints that we are going to work with, okay? Constraints is this, okay? No brick should be dropped. Even by mistake, okay? So in order to be very careful, right, as a follow up, until the brick is safely placed on a flat surface, you don't send the next brick in. Okay, so assume here that I have about 10 stairs like this, whatever, you go up to 10, and let us say that each person is now going to take 1 unit of time to actually collect the brick from a person on this side and give it to the person on the other side, right? So therefore, if you go by this logic, what you would do is you would feed the first brick into the system like this, okay, number 1, and of course, because the brick is in transit all through the 10 stairs, you cannot feed the next brick in, otherwise you run the risk of breaking something, okay? If the somebody is not doing it perfect, not doing a perfect job and stuff like that, it can be a problem. And therefore you are going to be very careful about this. You send the brick all the way, you make sure brick number 1 has arrived here, right? And then the second brick can now go into the system. This is brick number 2, right? So again it will take 10 units of time, and then you keep brick number 2 here, right? And then you feed 3, right? And eventually you will get all the 10 bricks on the other side, or how many ever bricks there are, you can have it transported into the system there, right? So if you ask yourself now, how many units of time did I take to transport 1 brick? Or in other words, I will ask a more interesting question. How long before I can send the next brick into this system, right? Because how long it takes is, of course, however long it takes for all these people to transfer it from the bottom to the top. So that is not going to change, right? Whatever you do, right? But the only question we can ask is, now, how long before I can send the next brick into this system here, okay? And the answer, going by this particular constraint that we have, is 10 units of time, okay? So T is 10 units, whatever the unit of time is, okay, 10 units of time. So the idea of pipelining is to actually improve this particular number, okay? Which number? The delay with which I can feed the next brick into this system, right? Like I told you, the delay that is going to that will be incurred in order to take the brick from the bottom to the top is fixed, because it has to go through all these 10 workers and eventually reach the top. However, if I am going to ask the question differently, when can I feed the next brick? Then I can do something clever, okay? So in order to satisfy this particular condition here, what I can do is somewhere here I will build one pedestal. Okay. So now what you are going to do is the following. The way you are going to do this is, you will send brick number 1 into this system. Okay. 1 to some 5 people or 4 people or whatever will carry it, and eventually the brick will come here. Okay. Now the brick has been placed on a flat surface on that pedestal, and therefore the next brick can come. So the person who is standing on this stair, right, on this stair, can, even if there is some slight delay, can turn around and still take it from this pedestal and give it to the next person. The brick will not fall and break. You are guaranteed about this. However, the constraint again here is, this pedestal can hold only one brick. Okay, you cannot keep accumulating bricks there. Only one brick. When by the time the next brick comes, the older brick should have gone. Okay. So now what you do is, in this situation, the second brick, right, can actually be sent into the system as soon as the first brick has been placed on that pedestal, right. Now, while the second brick is making its way up to this pedestal, the first brick will be making its way up here. Okay, and therefore eventually you will see that brick number 1 comes here. Okay, and then by the time brick 2 is here, then you can feed brick 3 into the system here, right. So likewise, you will, you will continue doing all these, exactly this job, and you will eventually get all the bricks here. But now the waiting time has come down. I don't have to wait 10 units of time, right. So let us say, for example, this is number 1 to 2 3 4 and number 5. At step number 5, I put that pedestal where I can place that brick, right. Therefore technically I can feed the next brick after 5 units of time. This delay has now come to 5 units of time. Okay, so this is the exact idea of pipelining, right. So what we are going to call, this delay, right, the delay with which you can feed the next input into the system, as throughput. Okay, and the delay, so if you ask yourself, okay, when can the next brick come into the system? Yes, it is after 5 units of time. But how long does brick 1 take to go all the way to the top? Of course, it takes all the 10 units of time, plus any delay that is incurred in placing it on the pedestal and taking it off that blue pedestal, right. So this is called throughput, and this delay, the delay that it takes to actually go through the entire system, is called latency. Okay, so latency and throughput are two numbers that we will be talking about when we talk about the idea of pipelining. Okay, now I will introduce a more interesting problem into this whole setup here, right. Initially, I assumed that all these workers are very similar, and they take the same amount of time. Okay, and therefore I said everybody takes 1 unit of time. Now let us say that that is not the case. Okay, let us say that that is definitely not the case, and maybe I'll make a copy of this as usual. Okay. Okay, I'm going to take this off. Now I am saying that, okay, I'm not sure I want to place the pedestal here, because that depends on certain constraints. Let us say 1, 2, 3, 4, 5, 6, all these 6 or up to 7 people take only 1 unit of time, but number 8 takes 5 units of time. Okay, so let me put that here. This person here, 8, no, this is 8, right, 8. So here I am saying the delay TD is let's say 5 units of time. 5, 6, yeah, good, okay. And now I want to ask, the same question, okay. Where should I be placing this pedestal? Where should I be, when can I feed the next brick into the system, and so on, right? So what we did was, last time we just chose step number 5 because that seemed like a logical point to break this, right? And we said, okay, 5. Okay, so now you just consider the same scenario. Brick 1 comes, okay, and then I go and place brick 1 here. Now, can I feed brick 2 after 5 units of time? Okay, that's the question that we have to ask ourselves, right? So remember that as 2 is making its way up on those stairs, 1 also has to go, and there can be only 1 brick on a pedestal at a given time. Okay, so let us say, consider this example where we have placed this pedestal at step number 5. So it takes 5 units for this first brick to reach that pedestal. It is already on the pedestal, and the next brick is fed again after 5 units of time. Why? Because this is 5 units. Okay. On the other hand, on step 8, that person takes 5 units. The remaining 4 will take only 4 units. So if you see on this side, you have 9 units of delay. Okay. So for brick 1 to actually reach the top, it will take 9 units of time. Okay. So brick 1 comes, brick 2 enters after 5. Brick 1 is also making its way up, okay, but brick 1 has not reached the top when the third brick comes into the picture here, right? So the third brick is going to, when this is 2, number 3 comes here, right? The first brick would not have reached this point yet, because it is going to take 9 units of delay to actually get to the top. Right, within 5 units, the third brick is now coming into the system, and therefore clearly you can see that if this continues, eventually you will have piling up of bricks on that pedestal, and you're going to likely break them. Okay, and therefore this system is not going to work correctly, which means that where you choose to pipeline, where you choose to break and actually hold that brick is also very critical. Okay, it's not a trivial thing. So one thing that is intuitively clear is there is no point in breaking it asymmetrically, where one half takes one part, I'll not say one half, one part takes 5 units and the other part takes 9 units of time, right? The latency in both cases, by the way, is still 14 units. Okay, remember that, there's no doubt about that. But I'm just saying that it does not make sense to break it asymmetrically. And therefore, what you must do is try and break this at a point, let's say somewhere here. Okay. On the 8th step, I'll put it. That means there are 7 people before this. Okay. So let me redraw this up to this point. Seven units of time. Okay. And the second half is 8 plus 1 plus 1, right? No, it is 5 plus 1 plus 1. So that is also 7 units of time. Okay. So what we have done is we have placed this pedestal at a point where the delay is now again equal, okay, in both places, and therefore now if you ask when can I feed the next brick in, well, it is after 7 units of time. Okay. But in the previous case, suppose we had that pedestal placed only at the 5th step and it took 5 units to get to the first pedestal, and after that it took 9 units of time. Well, in that case, you will be safe only if you feed the next brick after 9 units of time, not after 5. Okay. Whereas because of this, appropriate optimal placement of the pedestal, we have been able to improve the throughput to 7 units of time as opposed to 9 units of time, even though we had an asymmetric delay incurred because of that one person, right? So this is again just an intuitive picture, right? Now you could take this further, right? I could break the pipeline and into 3 parts, into 4 parts, into 5 parts, all the way even up to 10 parts. Okay. So if you look at what happens in reality, okay, on a construction site, there is no pedestal, right? People just take the brick, they give it to the next person, they take the other brick, give it to the next person. They just work in perfect synchronization, and this is possible only because there are humans there who are constantly adjusting their delays so that they match the next person. Okay. So even if due to some reason one person is slightly slow or something like that, the brick will not break because the previous person will now adjust it. Unfortunately, logic gates and all that stuff cannot do that adjustment of delay. They have fixed delays in a given circuit, and whatever you get, you have to make sure you work with them, right? And therefore, it is not possible to do all these adjustable delays, and therefore you cannot pipeline it like that without any pedestal. You got to put some pedestal somewhere, and every time you put a pedestal, there is some delay and area also incurred, right? You incur a penalty in delay and area, like adding a pedestal, you have to build some pedestal there, right? So it's, if you want to add 10 of them, well, you have to pay the price of adding 10 pedestals and also the delay of putting it there and taking it back and all that stuff, right? So in some sense, this analogy is only to give you um, an idea of what the concept of pipelining is, and also you note here that this pedestal is now used to actually sequence these bricks. You have bricks 1 to 8, they need to go up in exactly the same order, right? So 1, 2, 3 and all that stuff will go exactly in this order, they get accumulated like this, and so on, okay, as given here. And this will really solve the problem based on the constraint that we imposed here, right? So now let's take this analogy and map it to the concepts that we already know, right? The idea of a person who's receiving the brick and trying to give it to the next person is exactly like a combinational block. You have an input coming, the change in input causes a propagation through that circuit, and the output changes after a certain delay and will stabilize to some particular value, right? So this is what we call static timing analysis. There is a maximum delay, right, through that circuit, or the critical path delay, which will determine how slow that circuit can be, and therefore worst case that the output will be ready only after that delay. Okay. So each of these guys are like combinational blocks, C1, C2, C3, C4 and so on, right? What is our pedestal? This is nothing but a flip-flop. What is a flip-flop doing? It is just storing data. The brick is basically the data for you, right? You either have the brick or you don't have it. So you're going to store that brick there, or and you're going to then send it. So in this case, we are just talking of sending a sequence of ones, really, right? You're going to store that brick and send it up further, right? The pedestal does nothing but receive that brick and then store it until the next person can take it, right? That's the basic idea. So in some sense, the original picture that we had, right, the original picture that we had here, okay, of without a pedestal and just the staircase with these workers sitting there, I mean standing on it, right, can be represented like this. Okay, so this is a flip flop. Okay, this is a clock. Okay, so all these flip flops that I'm talking about are D flops. Okay, so I'll just call it D here. Okay, and so this is combinational block, which is basically one after the other, C1, C2, C10. Okay, so where did these flops come from? Well, you see that you are able to store the bricks on the ground here. There is one pedestal for you to store these bricks, and then there is another pedestal for you to store the bricks on top as well, right? So these are like buffers for you from which you are collecting data and just sending. So therefore, you can model this as a flop in the beginning, series of combinational blocks, and a flop at the end. Okay, and we said that the delay of these blocks is just equal. Everything is just 1 unit of delay at this point, right? Now, what we are saying is, I will add another flop, and therefore, if you ask what is the throughput of this system, right? What is the throughput? It is the time at which the next input can be fed into this system, right? So that there is no contamination of data of the previous evaluation. So data 1 comes in, right? That's your brick 1. Until brick 1 goes on top, you don't want the next data to come in. That's the idea there. And you therefore you have to wait at least 10 units of time. I am not talking about the sequential overhead, delay overhead because of the flops. I'll come to that later, right? So you have to wait at least 10 units of time, right? Now we are saying you take this guy and you break it like this. Right, 1, 2, 3, 4, 5, right, C1, C5, and add another flop here, okay, a pedestal here. Again, this is C6 all the way to C10, and you come out of this clock here, okay. So if you ask yourself how long does the data take to come out of this system, well, it's still the same 10 units of time, but I can now feed the next data after 5 units of delay, right? On the other hand, remember, if there was that asymmetric delay, right? For example, this was only 5 units, right? And this was 9 units of delay, then I can feed the next data into the system only after 9 units. Okay. Therefore, the third modification that we studied was to optimally place this guy. I collect 2 more C1, C2, C7, right? This is my clock. Then I have 3 more guys, C8, C9, C10, okay, and then okay. So the delay here now is 7 units, okay, and this is 5 plus 1 plus 1, which is also 7 units, and therefore there is an equal delay. So the throughput uh, equal to 9 units, okay, whereas throughput here is 7 units, right? The latency in both cases, latency 14 units. That doesn't change irrespective of how you are placing the flops and so on. So like I said, if you go and place 10 flip flops like this, right, you will be able to actually improve the throughput to 1 unit of time. The next guy can go in immediately after the first brick has been sent in, and therefore the speed at which you can operate is much higher in spite of the latency still being the same 14 units of time. Okay, so that's basically what we had here.